In our second module of Module 6, we're going to look at some more rules. You're going to continue reading about these as you read through the modules 6.2 and 6.3 in your reading assignments. They don't exactly totally line up, but eventually you get to all these topics. So at any rate, in the previous model, we looked at the general addition rule, which is generally how we do or we deal with situations where there's more than one way for us to be successful. So, multiple ways of being successful for a single trial. For example, we looked at the probability of getting a king or a heart. The word "or" always implies that we have options of different ways of succeeding, of fulfilling the constraints of our event, so to say. So we said, what's the probability of getting a king or a heart? Well, the "or" means that there's more than one way that we can succeed. So we ended up adding up the probability of getting a king plus the probability of getting a heart. Now, when we add up king and the number of hearts, we actually end up over counting many times if they are not disjoint. And so we always add this little caveat to the end of it here in case, or at least for those situations where we do have overlap. When we subtract off the probability that A and B occur simultaneously, meaning in our previous example that we get a king and a heart, so we're meeting both requirements at the same time. There's only one card that did that, and that coincides with the number of our overcount back here. So by subtracting that out, we canceled out that overcount that we made, taking it from 17 to the correct number of cards. That would be either a king or a heart, which is 16. So this little part here is why we call this the general rule for probability. If the two events are disjoint from each other, then the probability of A and B occurring at the same time is 0. And we saw that in the example of picking a 9 or a queen. There is no nine of queens, so we would be subtracting 0. And so this is a formula that we can use for both disjoint and non-disjoint events. So then what about situations where we have more than one event occurring? Situations where we have one event followed by another event. In those cases, there's two important definitions we have to look at. And these are different than the idea of disjointedness that we looked at with the addition rule. When we have sequential events, meaning one event following another event, we say the events are independent if the outcome of the first doesn't affect the probability of the second. We can look at a deck of cards, for example, and know that if we draw a card and then we replace it, then once we go to do the second draw, so meaning we're doing more than one trial in a row, if we replace the card, then the probability for my second draw does not change. However, if we don't replace the card, then the first outcome ends up changing the probability of the second. And that is something meaning that the probability actually changes for that second. There's fewer outcomes now possible in the sample space, and so we have a different probability now for our second event. And this applies for more than just two events. You can have 3 sequential events. So in other words, you're picking 3 cards from a deck and so on and so forth. So if we have 2 independent events, E and F, so we're just using different letters here, but let's say we're picking 2 cards and we have E and then F followed by F. In these cases where we have one trial followed by a second, we're always going to multiply those trials. This is to, contrast with our previous example where we were drawing one card, but we had 2 ways of being successful for that single draw. Here we actually have 2 events occurring, so 2 trials, one following another. The key word, if they're independent,
then one occurs and then another occurs in that order, and this becomes more important as we go here, the first event doesn't affect the probability of the second. So let's go back to cards and look at an actual example here. If we chose 2 cards from a standard deck and we replaced them as we drew them, what's the probability of choosing a king and then a 10? I want to point out the specific wording there that we're choosing a king and then a 10, which implies king came first and 10 came second. Well, when that's the case, this is a perfect example where we can apply the multiplication rule. We're first going to pick a king and then a 10, so we are going to take the probability of getting a king and multiply it by the probability of getting a 10. Since the probability of getting a king is 4 out of 52, and the probability of getting a 10 is also 4 out of 52, we're going to multiply these two. This is for my king, and this is for my 10. And that gives us, well, these reduce down to 1 out of 13, because 4 goes into 52 13 times. Whoops, so that should be 1 out of 13. And that gives us 1 out of 169. These are things you can simply type into your calculator and get the decimal equivalent, which is 0.006, if we took it to the tens, hundreds, thousandths spot there. On your calculator, if you want to take it back 2 fractions, if you hit math, I know it's crazy, you have a math button on your calculator, but it's on the far left side. I believe it's underneath the alpha key, math, and then you'll see frac, so choice number 1. And if you hit that, and sometimes you have to hit enter one more time, it'll actually turn it into a fraction in lowest terms. And in some of your boxes in WAMAP, if it has a preview button next to the box, you can actually enter these as fractions, which is kind of a handy little thing. All right, well, that's a very specific outcome for a very specific order. But what if we had worded it just a little bit differently? What if we had said, what is the probability of selecting a king and a 10 within 2 draws? And so this suggests that it doesn't really matter whether the king comes first or the 10 comes second, but rather just by the time we draw 2 cards, that we end up with a king and a 10 in our hand. In this case, there's actually 2 ways for us to succeed. We've already seen one of them, and that was the probability of getting a king and then a 10. And we just found that. However, if order isn't important, then we have another alternative way to be successful. So again, we have options. That means we use the word or. We could also get a 10 followed by a king. Notice that these are 2 specific outcomes, and they're different, but they both satisfy the event that's being described. And if we were to find the probability of king and 10, or 10 and king, sorry, all we would be doing is switching around these 2 fractions as we multiply, and in multiplication, order, of course, is not important. 2 times 3 is the same as 3 times 2, hence 1 over 13 times 1 over 13, even if they weren't the same fraction, comes out to the same product. And so they both come out to 0.006, or implies, of course, that we add. These are 2 paths of being successful, and so both of these need to be added together to get our true probability here of 0.012, which is 1.2%. So as you see, reading the question very carefully is extremely important, because sometimes the order is not important, and so therefore if it isn't, we have to figure out each path in which it could happen. In this particular example, we're going to look at blood type, and we have the population broken down into the different blood types, O, A, B, and AB. And you can see the different probabilities, which relate to the percent of the population that meets those requirements. And so if I were to say what's the probability of somebody having blood type A, then it's going to correspond to the percent of the population that, of course, has that blood type. That becomes our probability. So population layout, as a general idea, within large populations becomes the probability of selecting one person at random and the probability of selecting that person with that quality. But if we're selecting two people simultaneously and at random from all people in the United States, the question here is what's the probability that both have blood type O? So two people are being selected, meaning we have two trials or two events, one following the other. Now here's a question for this particular scenario is, are these two events independent? Or are they dependent? In other words, if we select somebody from the population, does that mean that we have one less person to select from, and hence does that change the probability for the next person that we're going to select? Which on a purely technical level, yeah, if we take out one person, that's going to eliminate one person from our population sample space, right? And so we'd have one less person to select. So on a technical sense, you could say that would be a dependent situation. However, if we really look at the probabilities surrounding taking one person from the population, we would probably say that it really doesn't make a difference. It would make a difference in such a minute way that in essence, it really doesn't change the overall probability. So we're going to consider these events independent. When we select from large populations like people from the United States, we generally just ignore the idea that we'd be changing the population layout. Okay. So, I'll get back to my pen here. If our probability is to find the probability that the first and the second person both have blood type O, we say, well, for the first person, their probability is 44%. And for the second person also, their probability is 0.44%. In fact, when we multiply similar numbers multiple times, we can always also just take 0.44 and raise it to the second power. And it comes out to about 19%, 0.19. So approximately 19% probability of that occurring. Usually probability, we're going to round this to 4 decimal places. But in this case, I just rounded it to 2. All right, so let's explore this just a little bit more. And we're going to go back to the coin tosses and see what we can uncover with this. Move this up a little bit here. So if we toss a coin 3 times, we saw earlier in 6.1 that we can, or maybe it was module 5, I can't remember, but we saw that we could model the outcomes by drawing out a tree diagram like we have here. In a tree diagram, we see all the possibilities. So for 3 tosses of the coin, we can look at how many ends there are here for my tree, and that is, in a sense, the number of possible outcomes that we have for this particular probability trial of tossing a coin 3 times. And here what I've added also are the probabilities at each stage. Every time we toss it, the probabilities are the same, they're 1/2, which tells us that these particular trials are independent. This is helpful to us if we want to, for example, find the probability of one particular outcome. Here, if we wanted to find the probability that we get heads, and then heads, and then heads, which we can shorten that and just write it heads, 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 assuming that there's an and in between those, knowing that this first heads is the first trial, the second H is my second trial, and the third H is my third trial. We can see that the product, or the probability of that one particular outcome events, is 1/8. And so if we asked another question, said, what's the probability of getting heads, heads, and then a tails? Notice that the wording of that really implies that there's an order there. Heads comes first, the second heads, and then followed by a tails. So heads, heads, and then tails would be written as heads, heads, tails. And it turns out as we go through this, since each one still has a probability of a half at each and every turn, that also has a probability of 1/8. However, if this is worded differently, again, we have to reconsider our previous answer. If we were just asked the probability that if we toss a coin 3 times, we would get 1 tail within 3 tosses, and no order is specified there, and this is written incorrectly. I'm going to put a little T there to match the other wording. 1 tail in 3 tosses gives us 3 ways to be successful. Now, I don't care if the tail is the 3rd toss, but that is one probable outcome. I could get heads, heads, followed by a tail. But then I could also get heads on the 1st, tails on the 2nd, and then heads on the 3rd. Or another way I could be successful here would be to get tails first, followed by two heads. In other words, if we look back to our tree here, we see that heads, heads, tails is one path that leads us to success. Heads, tails, and then heads, but also tails, heads, heads. All 3 of those are ways that we could end up with exactly 1 tail when we toss a coin 3 times. Each one of these has a 1/8 probability, so that's 1/8 plus 1/8 plus 1/8 again, giving me a probability of 3/8, which in decimal form is exactly 0.375 or 37.5%. As you can see, order is really important. One of the things that you'll note here is that if we go back to the first probability that we had here at the top, that when we found heads, 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 we didn't have to worry about order because there's no way for me to uniquely range heads, heads, heads in a different way. And so heads, 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 when it was the same outcome, really only has one path. And that's one pattern that you want to take note of. A lot of the questions that you'll be asked sometimes especially as we're starting out through these, is similar outcomes. Tossing, picking 3 blue marbles, or etc. And whenever they are similar outcomes like that, there's only one path that leads us to that end. But whenever we have a mix-up of heads and tails or blue and green marbles and that type of thing, we always have to ask ourselves, well, okay, in this case, is order important? Because if I rearrange these, I actually have a unique and different outcome. Let's look at another example. This one's somewhat similar to what we just looked at. In fact, we can see that there's a similar tree. I've changed the letters. But in this question, we have a multiple choice test consisting of 3 questions with 5 possible answers, one of them being correct. So we have a multiple test that has 3 questions, and for each question there are 5 possible answers, with one of them being correct. So this is a test with 3 questions, and so we have 3 guesses that we're going to make: first question, second question, and third question. And along the way, we're either going to get the question correct or we're going to get it wrong. If we get it correct, there's a 1 out of 5 or 20% probability that will happen because there's 1 right answer out of the 5. But there's a 4 out of 5 probability that I'll get it wrong. And so you can see that even though these are independent, I don't have the similar probabilities along each path here as we did before with the coin tosses. First question says, what is the probability that the first 2 are correct and that the third one is wrong? Well, that's a very specific path. And if we look at that, the first 2 being correct, that takes us here and here, and then the third one being wrong takes us down to here. So we can look at those probabilities, but As you're doing this, you're not necessarily going to want to draw out a tree every time. So you can think of these as 3 trials. We know we're going to multiply them because we are multiplying as we go. 3 separate events. The probability that the first one is correct is 1/5, second one correct, 1/5, and then the fourth one, or the third one, sorry, I just added another question there. The third one being wrong is 4/5. And so we look at that, and that's a 4 out of 125, which if we take that and turn it into a decimal, we get 0.032. So you can see there's not a very high probability that the first 2 would be correct and the third one would be wrong, which is pretty obvious if we're guessing on a test. Generally, that's not a good study habit and probably won't work out too well for us. However, this is a very specific order that we've dictated here. And it's probably actually a little bit better of a chance, though still a very low chance, that we could get 2 out of 3 correct. If, in fact, this had been worded differently and said specifically that we just got 2 out of 3 correct, you can see that there are a lot more than one way that can happen. I could have the first 2 correct and the third one wrong, just like we saw. Or, so plus, I could get the first one correct, the second one wrong, and then the third one correct. Or I could get the first one wrong and then the last 2 correct. You'll see that if we trace each one of these paths up here, doesn't really matter. I could get correct, correct, or I could get wrong, correct, or my original correct, wrong, and all 3 of those have 1 wrong and 2 correct. And they're all 4/5 times 1/5 times 1/5, which leads me for each one of these to be worth 4 out of 125. So that's 4 out of 125 added to another 4 out of 125, added to another 4 out of 125. Or we can also just go 4 out of 125 times the number of paths, because when we add the same number to itself multiple times, this is adding multiple numbers to itself, not multiplying 3 times. It's the same as going for over 125 times 3, which gives us 12 out of 125. So that is 9.6%, 0.096. So still less than a 10% probability of occurring, but much better, or somewhat better, than 3%. This is why we always need to think about, is order important? One more example I wanted to go over with this particular situation. Same situation, I haven't changed the numbers or anything like that. But here's a third question, which is an interesting question, and is something that we actually see pop up a lot more down the road as we move ahead. And you can see that when we start having more than one trial followed by another, these start to these trees will start to get long. Like, for example, here we have 8 different paths at the very end. But if we were to take it one more question or one more guess that you had to make, it would be 16 paths, and then 32 paths after that, etc. So it can start to get kind of crazy. Here's a principle that we're going to look at, kind of a general rule that you can use, and I'm going to give this one as kind of an example. What is the probability of getting at least one wrong, or one W in this case I've written it as? Well, if you think about having at least one W, the word itself, at least, is an interesting word, and we have to think about it. In fact, this is a word that you're going to see pop up a lot. What does it mean when we say at least one? It helps to kind of apply it in a situation where you just kind of automatically go, oh, okay, I know I understand that. Like if I said you have to have at least a 70% on this test in order to pass, you would say, okay, well, that makes sense. That means I have to have a 70 or above. So the word at least is actually the symbol greater than or equal to. I have to have a number greater than or equal to this number. So when I say at least one, that means 1W or 2Ws or 3Ws. If we look at the different paths that we have for those, we could say, okay, well, CCW, as we saw previously, that would have at least 1W. CWC, that's 1W, and CWW has 2. That's at least 1. Also, 1WCC, 1WWC, 1WCW, and WWW, all of these have at least 1W. And in fact, if I were to try to just do this by hand then, we would have many different answers here. We could have, just as I illustrated above, CCW, CWC, CWW, or we could have WCC, WCW. See, after a while, this kind of almost gets painful. WWC, or the last one, WWW. We would have to find the probabilities of each one of these paths. Notice there's 7 out of the 8 paths, and we'd have to add all of those up. But you'll notice one important thing is that this path over here, CCC, is the only path I didn't select. And here's where the complement rule can come into play and can be extremely helpful to us. Instead of finding all of these paths and adding them up, I could instead use the complement rule and find the probability of no wrong answers, and then subtract that from 1. This is the only path. These all add up to 100% or 1. So when I say no W, we think, okay, well, what does that mean? Well, that means, of course, that none of them are wrong, that they're all correct. Correct is my path. And that, of course, is 1/5 multiplied by itself 3 times. Correct. So that's 1 minus 1 over 125, which is 124 out of 125. And 124 divided by 125 is 99.2% or 0.992. There is a high probability that I'm going to get at least 1 wrong when I select 2, or when I select or I guess on 3 answers. So this rule we call it, or I call it, the at least 1 rule. If we ever have at least 1 rule, in general, in a situation where there's at least 1 success, and of course success is defined differently depending on the situation. In the last problem, our success was a wrong answer. Okay, so the complement rule is a much more effective way of finding the probability. Rather than find the probability of each path that has at least 1 success, whatever that success might be, and that changes from problem to problem, you can just kind of fill in the blank there. Here's how we would do it. The probability of at least 1 success is always equal to 1 minus the probability of no success. And a lot of times it's either success or failure, so you just have to find however many trials there are and how many failures you want in that case. In this last one, the failure was getting a correct answer. As you can see, failure and success have different definitions depending on what's being asked for in that particular problem. For example, if we were to go back to the coin toss, I could say, what's the probability that we get at least 1 head? So now we're calling a head a success. And in that particular case, we're flipping it 3 times. There's 7 ways, 7 paths that lead us and have exactly or at least one head. And so the better way to do this would be to go 1 minus the probability of no heads. And the probability of getting no heads is the same as getting all tails. So tails, tails, tails. And we talk about that. 1 minus tails, tails, tails had a probability of 1/8. So the probability of getting at least one head is 7 out of 8. Much simpler than finding and adding all the probabilities of all of those paths up. And if you forget one of the paths, if you don't have a tree there, it's really easy to do that. Then, you get it wrong because you forgot one of the paths. All right. We didn't as much talk about dependent events, but this is a really important idea. In dependent events, everything we've looked up to now have been independent events, but the basic rule is still the same. The probability if 2 events are dependent meaning that when one occurs, it actually changes the probability for the next one. The probability for E and F is equal to the probability of E times the probability of F, but then we throw this little caveat in here, this little line, and that line means given E. And so the way we interpret this, it's the probability of F given that E has occurred. So we simply want to look at, by E occurring, assuming that this E occurred, how does that change the probability for F? And if it does, we change it. We're going to look more into the meaning of this in Module 7 and how we can kind of codify that into a formula. But with sequential events, one following another, generally it's pretty easy to interpret that because we just assume E has occurred and we change our probability here, assuming that to be the case. For example, what is the probability of choosing 2 face cards in a row, assuming that the cards are chosen without replacement? So now we're back to a deck of cards again. We want to know what's the probability of choosing a face card and then another face card, assuming that a face card was chosen first. So we're going to go face, probability of face, multiplied by probability of a face card, assuming that we picked a face card on the first draw. In this case, since we're not replacing them, that is going to change my probabilities. The first face card, there are 12 face cards in a deck of cards. 12, there's 4 kings, 4 queens, and 4 jacks. So when we say face card, we literally mean a card with a face. On the first draw, there's a 12 out of 52% probability that we're going to get something that has a face card on it, or that is a face card that has a face on it. And then for the second one, assuming that a face card was chosen first, we say, okay, well, that means there's one less card in the deck, so now my sample space has changed to 51. And assuming that we chose a first face card on the first draw, now we have an 11 face cards left in the deck. And so that changes that top part as well. That's not always the case, so you always want to be careful about that. Sometimes only the sample space changes and not the event space, but in this case, since it was 2 face cards in a row, it did change. And if we multiply that out, we get 0.049 and 8, rounding that last number up. So, pretty interesting there. Now, this actually is what we call the general multiplication rule, because we can actually use this in any case, whether they're independent or dependent. Reason being is if they are independent, the fact that E has occurred doesn't change the probability for F because they're independent. And so we can actually use this rule every time. And in fact, it's good to think of this because it actually makes us think about, hey, is the probability has it changed? And if so, how has it changed it? All right, so let's go back and just kind of go over some ideas about disjoint and independence within two events. When we talked about disjoint, these two concepts are very different, but they're easily confused with each other. So it's really important that you understand and know the difference between them. When we talk about two events being disjoint, we're talking about the two events cannot happen at the same time. This would be like picking a card and having it be a 9 and a queen at the same time. We say two events are independent of each other if the two events where the probability of one event does not affect the probability of another. Two events are independent, such like flipping a coin. It doesn't matter how many times I've gotten a heads, I'm not due for a tails, right? The probability remains 1/2 regardless, and it doesn't change. So we're going to look at a few examples here, and we're going to decide whether they're disjoint and or independent. Two people are selected from the population and their blood type is checked. Event A is that person 1 has blood type O, and event B is person 2 has blood type O. So we're selecting two people, and we want to decide first, are they disjoint or not disjoint? So if we think about that, two people being selected, is it possible that we could get two people that both have blood type O? And if it's possible, that means they are not disjoint. Yes, this is possible. We can end up with two people with blood type O. That isn't impossible to occur. That means they are not disjoint. And the question is, are they independent or dependent? Since we're selecting them from the population, and a population is very, very large, we don't know how large it is, but we'll assume it's large, we'd say these outcomes are vastly, really independent of each other, because it doesn't really matter if we have such a large population. The second one, a seminar consists of 5 males and 5 females. Two people, again, are chosen at random. Event A, the person is male. Event B, the person is female. Had to move things there a little bit. All right, so two people being selected, are they disjoint or not disjoint? Is it possible for me to pick two people and have one be male and one be female? Of course, we know that that's true, and so we would say these events are not disjoint. Are they independent? Does choosing a male on the first pick affect the probability of choosing a female on the second pick? And the answer is yes, it does. Because once I've picked a male, there are fewer males to choose from than females. And that takes our probability from 5 out of 10 to 5 out of 9. So because the probabilities change, we say these two events are dependent. For the last one, a telemarketer is calling a randomly chosen phone number. Event A, the person answering is male. Event B, the person answering is a female. So, first question is, are these disjoint? Notice that unlike the other two examples here, we are calling a randomly chosen phone number. I mean, we're just calling one number. Is it possible for the person answering to be male and female at the same time? Notice it says person answering. And unless you're like my parents and I call and they have me on speakerphone, this is not really possible, right? We can't have both occurring at the same time. So we would say that these two events are, they are disjoint. Sorry, not disjoint. I was circling the wrong one. Let's uncircle that. These are disjoint. They cannot happen at the same time. Second question, are they independent or dependent? We know that there's a 50% probability of this occurring and a 50% probability of this occurring, all other things being equal. So, do those probabilities change if event A occurs. In other words, if event A occurs, does that change the probability for event B? Now, this is a bit of a tricky question. If event A occurs, then, in other words, the person answering was a male, there is now a 100% chance of event A. And for event B, the person answering, if we're only making one phone call and the A has occurred, the probability that I would be speaking to a female or somebody who identifies as female goes down to 0. So the probabilities do change if event A occurs. The event B becomes completely different. In fact, it becomes impossible. And so we would say these are dependent events. They are not independent. We could actually see this kind of layout. One thing that we have all three examples that I've given you here. And the one thing that I want to point out is what cannot exist. If we know that something is disjoint, then it's impossible for it to also be independent. And vice versa, if it's independent, then it's also impossible for it to be disjoint. It cannot be both. It may seem at times, like that last example that we looked at, that it could be, but if you really look at it, it actually cannot. Those two cannot exist at the same time. I hope this gives you some things to look back on, and as you go forward, remember, these are just simple examples of the concepts that we want to get into our brains, and that you want to take these and apply these to the many different scenarios that you're going to encounter as you go through your homework. The topic may be different. We may be talking about marbles. We may be talking about people who own dogs and all kinds of things. But the innate concepts that we've laid out here are going to help you kind of power through some of those topics. Good luck. Thanks for listening.